And so Monday, we'll go ahead and get started. Monday we began to learn about modular arithmetic, and today we're going to talk about things that we can do with modular arithmetic that help us explore properties of integers. And we'll talk about divisibility rules later on. Let's go ahead and get started. Go ahead and take a look at problem number 1. Okay, we want to find all possible units digits of perfect squares. So I'm going to start by asking the question, if modular arithmetic is going to help us, what modulus do we want to work in?
I think we'd work in modulo 10.
Yeah, modulo 10 gives us units digits. It tells us the remainder when we divide an integer by 10, at least usually with positive integers. What is -3 modulo 10?
7.
7. Good. So modulo 10 doesn't give us units digits with negative integers, not necessarily at least, but it does with positive integers. So we're dealing with perfect squares, so we're dealing with positive integers. And now let's explore. I'm going to let each of you work on your own paper and tell me what you think is true about units digits of squares.
They either end in 0, 1, or 6 or 9.
Whoever that was, is that Telvin? I could barely hear you. Can you move closer to the microphone?
They either end in 0, 1, 4, 6 or 9.
You're close.
It's either 1, 4, 5, 6, or 9. Or 0.
Or 0. But we do have to include 5 in there. Four squared is 16, so we have a units digit of 6. 5 squared is 25, so we have a units digit of 5. And this is it, by the way. 0, 1, 4, 5, 6, 9. How do I know I can stop here? I haven't squared all the different residues modulo 10, have I? What happens from here on out?
It gets reversed, where it becomes 6, 9, 4, 1, 0.
That's true. Is there any way that we could know that it's going to be reversed? So we want to square all possible residues. If we square all positive residues, we're squaring all possible integers, modulo 10, right? Because every integer has one of the 10 modulo 10 residues. But we're squaring. So most of the time we want to work with residues because those are simplest. But every now and then it helps us to say, hey, this residue is congruent to this negative number. And that's actually more convenient because we have already done those calculations. And that's why we get that mirror image. At least 1 through 4 is a mirror image of 10 through 9.
Mr. Crawford, why are you writing negative integers? Couldn't you just put 4 squared there or 3 squared there?
Well, negative 7 is congruent to -3, correct?
Yes.
So 7 squared is congruent to -3 squared.
Yes.
And that's the same thing as 3 squared, because the negatives, negative times a negative is a positive.
Okay.
So what we're doing is we're seeing a symmetry. And understanding that that symmetry exists helps us understand that we don't necessarily have to do all this work, right? I didn't necessarily have to square 0 through 9. I could square 0 through 5 and stop, because we know that squaring 6 through 9 is the same as squaring 1 through 4, just in reversed order because of those negatives. And that's a nice thing to notice, right? It means that we have to do less work in the future. So now let's answer question B. What about a perfect fourth power? What are the possible units digits?
Six and 1.
There's a little bit more than 6 and 1, but I think I know what you've just done.
6, 1, and 5.
Closer.
6, 1, 5, and 0.
6, 1, 5, and 0. And one nice thing about this is we now only need to square the results of our squares, because any number to the fourth power is the square of a square. So if we take the units digits that were answers from A and square just those, we should get all the units digits that could possibly be for a perfect fourth power. For instance, 6 to the fourth power is 6 squared squared, and 6 squared is 6, so that's just 6 squared, and that's 6. And since 4 squared is 6 and 9 squared is 1, we wind up with an even smaller set of possible units digits, smaller set of residues modulo 10. Any questions or thoughts about this? So if you ever see an integer, no matter how big, you don't really have to test so much if it has a units digit of 2, 3, 7, or 8. Those are never, ever perfect squares. Now, there was a problem like this before camp. Anyone remember which problem I might be referring to?
Could you please repeat that?
Sure. There was a similar problem that was asked on the message board prior to the start of camp. And I didn't do a full video on that one yet, because I knew that we would get to this point in discussion of modular arithmetic, but it had to do with units digits of a sequence. Do you remember which sequence that was? It was the triangular numbers. It was numbers in the form 1 plus 2 plus 3 plus 4 all the way up to n, or numbers that are in the form n times n plus 1 divided by 2. And whoever it was who posted that and asked the question about it, now you have a tool to explore with. And, I would say go back, work on that problem, see what it is that you can do. Non-Norley, was that you who posted that question?
Yeah.
So go back now and see if you can go through casework with modular arithmetic in some way to come up with the answer. Okay, let's take a look at another one. Number 2. So what modulus are we working in? Somebody tell me what modulus we're working in order to examine what's going on in this problem with units digits.
Is it 10?
We're working in 10 again. Good. Okay. So we write the congruence a squared b is congruent to 99 to the 99th power modulo 10. And I don't feel like computing the nearly 200 digits of 99 to the 99th power. So somebody help me out. What's that going to be equivalent to?
It's gonna be one. No. Yes. It's gonna be 1.
So Rishit, how do you come to the conclusion that it's 1?
Because no, it's gonna be 9. It's gonna be 9.
Okay, how come 9?
Because when you do 9 to the power of an even number, it'd be 1. But then when it's 9 to the power of an odd number, it'd be 9.
Okay, so you simplified 99 with 9.
Yeah.
Okay, and then you found a pattern. Good, we can do that. Anyone else have another method? Think about what we did.
99 is the power 99 by 10.
Somebody, I began talking over you, so unfortunately I didn't hear you. Repeat that for me.
You could divide the 99 raised to the 99 by 10.
But what can we do in the modular arithmetic?
We could convert 99 into its residue to determine what it's congruent to.
We did that. Rishit did that for us and reduced 99 to the 99th power to 9 to the 99th power. But there's something even simpler. What could be simpler than using a residue?
We could use the division theorem.
The division theorem is going to associate us with the residues. The remainders in the division theorem are going to be the residues. But there's something a little more clever. Look at what we did with the last few squares in the previous problem. What did we do?
Made them congruent to negative integer squared.
Right. And what is another integer that is equivalent to 9 that is easy to take powers to?
-1.
-1. Yeah. 9 is congruent to -1. So we could just say this is -1 to the 99th power. So a squared b is just congruent to -1, or we could say that's congruent to 9. Now we can bring it back positive and work with it. So you don't always have to do all your modular arithmetic with positive numbers. Sometimes you can find an easier way to make use of negative numbers. Okay, so a squared b, and we're told that b has a units digit of 1. So this is really just a squared 1, or a squared is congruent to 9 modulo 10. So what could a be modulo 10?
It
A
has to be a
would be
number that when squared would give us a units digits of 9.
That's right.
so 3 or 7.
So
3 or 7. 3 and 7 are the possibilities.
Or negative 3 and negative 7.
Well, at this point, we're asking what are the possible, find the sum of the possible values of the units digits. And the units digits aren't negative. The
Oh,
digits
yeah.
are positive. So that's the way we'll answer the question, but we can just look back up here and check our work from previously. And our answer is 10. Continuing along, we have a whole bunch to check for 3. Okay, what could a perfect square be modulo 3?
Is it 0?
0 is possible,
And 1?
or 1. Yeah, we
For
just go through
3,
all
for
3.
modulo.
Yeah, we just go through all 3 possible cases here. We square 0, we square 1, we square 2. We have now squared all possible integers, at least modulo 3. These are the only cases. Every integer is 0, 1, or 2, modulo 3. And we square those and we end up with 0 and 1 as possibilities. So if you ever see a number that is 2 more than a multiple of 3, you know absolutely for certain that number is not a perfect square. 11, 14, 17, 20, 23. That sequence, all those integers are not perfect squares. So let's do B. What are the perfect square residues modulo 4?
Zero, zero, 1.
0 and 1 both work. Oh yeah, those are the only ones, aren't they? Well, that's nice. Yeah, 0 squared is 0, 1 squared is 1, 2 squared is 0, and 3 squared is 1, modulo 4. So every perfect square is either a multiple of 4 or it's 1 more than a multiple of 4 if it's odd. Okay, how about 5?
Zero, one, zero, one.
Oh, David, I have an echo from you.
I think he said 0, 1, 0 or something. I think that's what he said. I don't remember.
Sorry, my laptop seems to be having a problem. That's why I have 2 users here. I meant to say 0, 1, 4.
0, 1, and 4 is correct. Good. I'm going to say you're never going to have much more than about half of the possible residues, because we're going to have that effect where we start squaring numbers at the end that are the squares of negative versions of the early residues, right? Like modulo 6, 1 squared is 5 squared, modulo 6, because 5 squared is negative 1 squared. So for 6, there turn out to be 4. I'll go ahead and mention that. I won't make you work that one. It's one more than half of the possibilities, just like we had 6 possible units, digits, modulo 10 for squares, 6 possible squares of residues, modulo 10, one more than half. That's the most we can ever wind up with. How about modulo 7?
5 possible residues.
Oops, I wrote something down wrong up here and I just saw my mistake. There we go. Okay. Modulo 7 residues of perfect squares. We're always going to have 0 and 1. What else do we have?
0, 1, 2, 4.
0, 1, 2, 4 is correct. How about modulo 8?
Zero and 4.
Yeah, that's kind of nice. When we get into problems later, we may see this, but modulo 8 is one of my favorite mods for examining properties of perfect squares with. And the reason is because there are just 3 possibilities, and out of 8, that's pretty restrictive. There are a lot of integers just based on the remainder when we divide by 8 that we could rule out as possibly being multiples of 8. As possibly being perfect squares. Okay, let's keep going. 9.
Zero, 7, 3.
0 and 7 both work. 0, 1, and 7. Any others?
5.
4 and 5.
I don't think we get 5. What could we square to get 5 modulo 9?
Sorry, I meant 2.
What could
When
we
you
square?
square 4, gives you 16. And when you square 4, it gives you 16. And if you try to divide, you have, sorry, I made a mistake, 7 left over, sorry.
16 is 7 modulo 9. Turns out we just have 0, 1, 4, and 7. And I'll point this out. A multiple of 9, actually, I'll write this down. If we have some perfect square, and we can write it, let's say we can write it as 9 times an integer plus 1. In other words, it is congruent to 1 mod 9. We could rewrite that as 3 times 3k plus 1. Oops, I meant the plus 1 outside of the parentheses, which means that it is 1 more than a multiple of 3. Also, 9k plus 4 is 1 more than a multiple of 3. And 9k plus 7 is 1 more than a multiple of 3. So if we look at part A on this, what we can see is that 1, 4, and 7 are all part of 1 mod 3. Did I make that clear?
Yeah.
And otherwise, we have a multiple of 3. And a multiple of 3 squared is going to be a multiple of 9. Okay, 10. Well, we've already answered 10, haven't we?
0, 1, 4, 6, 5, 9.
And there it is. And now finally, let's do 16.
Zero, 1, 4, 9.
And that's it. Notice that 0, 1, 4, 9 are the squares of 0, 1, 2, and 3. And so, one thing that we can notice is within a certain modulus, we always get all the squares less than that modulus, including 0. There's no simplification that needs to be done for those. So, that kind of tells us some that must be in that set. So good. These are restrictive, and we're going to see some problems where we practice using the restrictiveness of those mods. But first, let's take a look at, actually, we'll bounce around. I want us to get a little practice from that. Let's take a look at problem number 7. This seems like such a challenging problem. After all, there are infinitely many integers, a and b, that we could square. And there are infinitely many pairs of those squares that add up to multiples of 3 when we add them together. What do we know about the squares of integers modulo 3?
If they are multiples of 3, they have a residue of 0.
True. What can we say about this perfect square modulo 3 from our work earlier?
It only has residues 0 and 1.
It only has possible residues of 0 and 1. So I'm going to try that for each a and b. I'm going to say a squared is 0 and b squared is 0 modulo 3, in which case a squared plus b squared is 0 plus 0, which is 0 modulo 3. Okay, that was case 1. What's another case?
A squared is equal to 1, B squared is equal to 1 mod 3. That means A squared plus B squared is equal to 2 mod 3.
Okay, any other cases?
A squared is equivalent to 1, but B squared equivalent to 0.
Good. And finally,
A squared is 0, B squared is 1.
right? And I'm going to write this one out more completely. I'd been leaving mod 3 off for the a squareds just because I was following it up with the b squareds, but just to be most correct about the way I'm writing this, I'll always write mod 3 if I'm being most correct. So we see that in only one of these 4 cases do we wind up with a sum of squares having no remainder when we divide by 3. So it is a multiple of 3. That's the only case. And in that case, a squared and b squared are congruent to 0 mod 3. How does that help us prove the proposition?
It means that since a squared is equivalent to 0, it's a multiple of 3. And b squared is equivalent to 0, it's also a multiple of 3. And since you add the 0 and get 0, meaning the addition of their squares are also multiples of 3.
Yes, and we have to refer back to this casework where we squared all the residues modulo 3, and the only one that works is 0. 0 squared is 0 modulo 3, so any perfect square that is a multiple of 3 is the square of an integer that was a multiple of 3. I guess we could do that with divisibility also. I guess we don't really need modular arithmetic for that step. But yeah, this is what we can do. This is how we can be restrictive, or we can make use of the restrictive residues of perfect squares. Okay, so let's go back to problem 4 now. If we can find residues of squares, we can find residues of cubes. And maybe that'll be interesting also. So when we cube all the modulo 3 residues, well, we get 0, 1, and 2. Okay. So that wasn't really restrictive. But it is kind of interesting that the residue of a cube, modulo 3, is the residue of the original number that was cubed. So that's nice. So if I take like 11 cubed, which is 2 modulo 3, 11 cubed is 1,331. And I already know that's going to be 2 more than a multiple of 3.
Please, why is the 1 cube congruent to 1 more 3? Because when you divide 3 divided by 1, you don't get.
Nah, Norley, your microphone's a little bit faint. I have a little bit of trouble hearing you. Can you speak up?
Why is the 1 raised to the power 3 congruent to 1 more 3?
Oh, 1 cubed is 1 times 1 times 1. So that's just 1. Did that answer your question?
Yeah.
Okay. So now, modulo 4. What are the cubes modulo 4?
0 and 1.
I get 0, 1, and 3. Anyone
Yeah,
else?
sorry, I miscalculated a bit. Yeah, 0, 1, and 3.
Okay. How about modulo 5?
Zero, 1, 3, 4.
I agree that 3 and 4 are in there. Is there nothing that we can cube that gives 2 mod 5? Just cube all 5 residues, 0, 1, 2, 3, and 4. What do those turn out to be modulo 5? Oh, Sneh, you said something, but you cut yourself off, I think.
Sorry.
Okay, yeah. 27, so that's 3.
27. 3 cubed is 27, which is 2 modulo 5. So yes, we can achieve 2. And then 2 squared is 8, which is 3. And 4 squared is 64, which is 4 modulo 5. So we can get all possible modulo 5 residues. Oh, that's nice. Okay, modulo 6.
I think it's 0, 1, 2, 3, 4, 5, 6.
Yeah, once again, we can get all. I'm going to circle the
can't
ones
get
where we get
6.
all. Sorry?
And here he mentioned 6, but you can't get 6 because it's modulo 6.
Yes, sorry, that was a mistake.
6 is just 0 modulo 6. 6 is not the residue. 0 is the residue. It's like remainders. We only go up to 1 less than the divisor when we're doing remainders. With residues, we go up to 1 less than the modulus. And just in case I didn't make that clear on Monday, the modulo, let's say 12 residues are all of the integers from 0 to 11. The modulo 6 residues are 0 through 5. So how about 9? What are the residues of perfect cubes modulo 9? While you all work on 9 and 10, I'm going to refresh my drink. I'll be back in one moment. Anyone have a complete list of residues of cubes modulo 9?
9 is 0, 1, and 8.
1, and 8.
Yeah. Okay, we have one that is restrictive. That's the first one where it's only like a tiny fraction, or a small-ish fraction, maybe not tiny, but they're just 3. That's nice. What about modulo 10?
Zero, 1, 2, 7, 8, and 9.
I think we get more than that.
Zero, 1, 5, 6, 7, 8, and yeah, that's it.
We get even more than that.
I think it's 0, 1, 2, 4, 5, 6, 7, 8, and 9.
Everything but 3?
Yeah.
What is 7 cubed modulo 10?
43.
What is 7 times 7 times 7?
That's
343.
343.
343,
Three
which is
plus
3
four.
modulo 10.
That's
So 0 to
10, yeah.
9.
3.
Yeah. So all possible residues is what we get. Okay. So let's talk about these interesting cases where we have all possible residues still in a modulus. And I'll say this, 2 and 5 are already such mods, and 2 and 5 make up 10. And while it's a longer story as to why, that does, the 2 and 5 are really what we're doing here. We get all the combinations of residues modulo 2 and modulo 5, and that those give us the residues modulo 10. So, is there something interesting? Well, let's see. Does anybody have a calculator on them?
I have one.
Okay. Rishit, I want you to take a 2-digit number. Don't tell me what it is.
Oh,
Take a
okay.
2-digit number and cube that number on your calculator and tell me the result.
3,481.
3,481. Are you sure that's the cube of an integer?
Oh, my bad.
I think you squared 59, didn't you?
Yeah.
Okay, pick a different number.
Okay. 262,144.
262,144. You got the hiccups?
Yep.
Is that is the cube root 64?
Yeah.
Okay. Let's do one more.
Okay. 50,653.
37?
Yeah.
Okay. Actually, let's do something even bigger. Let's try one that is cube a 3-digit number.
Okay. 242970624.
Okay, I was struggling to keep up. Did I get this right?
Yes.
Okay. Is that 634?
624.
Oh, 624.
Yeah.
Yes, okay.
How?
Okay, so let's talk about this, and I'll explain to you why it is that that I got the last one off by just a little bit. If I'd taken my time just a little bit more, I would have corrected the error, and I'll walk you through that. So here's the thing. If we cube all units digits, modulo 10, if we cube all the residues modulo 10, there is a 1-to-1 relationship right? All residues are outcomes, and so that gives us a one-to-one relationship. And I'll try to write this down pretty quickly. Everything here is modulo 10. Just going to skip writing mod 10 after it.
Excuse me, 4 is 4.
The 4 is 4. Thank you. That's right. So since we have this one-to-one relationship, I can go backward as well, right? The first one that Richard gave has a units digit of 4. It is congruent to 4 mod 10. And so I just matched it up right here. And I said, well, the cube root must have also been 4 modulo 10. Then, so I already knew the units digit. After that, I said, hey, this number is between 60 cubed, which is 216,000, and 70 cubed, which is 343,000. Right? I know my cubes from 1 to 9. And 9 cubed is 729. That's the biggest. I've seen those enough that I know them by heart, and I can quickly estimate. And that gives me the tens digit. So anything with 6 digits or fewer, if it is a perfect cube, if it has an integer cube root, I can come up with it in less than a second. With 50,653, I know that 3 corresponds to 7. So I knew we had a units digit of 7. And then I said 50,000, well, that's between 27,000 and 64,000. So for the bigger one, a units digit of 4 for the cube told me that we had a units digit of 4 before cubing. And then we're at 242 million, which is bigger than 216 million, but less than 343,000. And I was going to try to do a quick estimate. There are different things that you can do here. One, you can say how far of the way we are, and that will sometimes work. Notice that 242 million is about 26 million more than 216 million. Actually, it's about 27 million. And in total, to go up to the next cube of a multiple of 100, we're going up, what is that, 127 million? But we only go up here about 27 million. So 27 out of 127, well, that's between a fifth and a fourth. So we should be between a fifth and a fourth approximately of the way from 600 to 700. So that's probably where I should have started. And just to check, and I said 634, I think, the first time around. In order to check, one thing that we could do is check it out if there are 2 possibilities. We can check this out by maybe checking modulo 3 or modulo 9. 242,790,624 is a multiple of 3. And so I know that the original number that we're cubing must be a multiple of 3. 624 is a multiple of 3. 634 is not. Now this one definitely takes longer, but it's...
Hello guys, this is Nisar Ahmed.
Say that again? Was that you, Rishit?
Oh no, I think something happened. That wasn't me.
Okay. All right. So yeah, it's kind of a fun little game you can play where you can learn to take cube roots of perfect cubes, and that is because of this relationship modulo 3 where we can map, and the mapping isn't bad either, right? A lot of these map to themselves. And then a lot of them map in pairs, like 3 and 7, 2 and 8 map in pairs. And it doesn't take too long to learn them because, you know, some of the smaller ones you see often anyway. So this is one application of the fact that we cover all possible residues when we cube integers modulo 10. Okay, let's take a look at number 5. Oh, actually, we really already talked about that. In 3, everything was restrictive, and in 4, sometimes there were no restrictions. And that gives us different application possibilities. So now, problem 6. Show that 17 to the 2007th power plus 22 to the 2007th power is a multiple of 13. Wow, these numbers are gigantic. How can we get started?
We can break the numbers already given to us, regardless of their powers, into modulo 13.
Okay, let's examine these numbers modulo 13. Can we simplify anything modulo 13?
Well, in modulo 13, 17 is 4, and 22 is like 9.
Good. This is congruent to 4 to the 2007th plus 9 to the 2007th. And hey, we just knocked off a few hundred digits. We took 2 gigantic numbers and made them into less gigantic numbers. Okay. So we're still not there yet, but this is a start. What do we notice about 4 and 9?
They are perfect squares.
That's true. They are perfect squares. What else do we notice?
They're squares of primes.
True.
They sum to 13.
They sum to 13. Does that give anybody any ideas?
Well, 13 is 0, which means, and only way you can get 0 in a modulus is if it's the multiple of 13, which proves that when you sum 17 to the 2007 power plus 22 to the 2007 power, it's a multiple of 13.
Well, we can't just add 4 plus 9. I mean, we're taking 4 to a big power and 9 to a big power. Notice that 4 squared plus 9 squared is not a multiple of 13. It's not 0 mod 13. So just noticing that 4 plus 9 is 0 mod 13, that's not enough.
Anytime they are raised to an odd power, that number is a multiple of 13.
If you check a few possibilities, it seems that way. Maybe we're onto something, but we still need to prove that. What is one of the techniques that we've used in previous problems that kept us from doing quite as much calculation as we needed?
Finding the negative congruence number.
Yeah, checking out negatives. Okay. What's a negative number that is congruent to 4 modulo 13?
-9.
-9. Very good, Non-Orly. So all of this is just congruent to -9 to the 2007th power plus 9 to the 2007th power. And that's congruent to what?
Zero to the 2007 power.
Right. These are just additive inverses. One is the negative of the other. And thus we have shown this gigantic several thousand digit number that we started with is a multiple of 13. Okay. How about problem number 8? We take all the perfect squares and we convert them to base 8 numerals, and we convert them to base 7 numerals. What are those units digits? What do they represent?
Modulo 10.
Not modulo 10. The units digits of decimal numerals. The units digit of base 10 decimal numerals that we're used to, those are the residues modulo 10. But what are the units digits in base 8? Well, let's take a look at an example.
Is it 1, 2, 3, 4, 5, 6, 7, and 8? No, 1, 2, 3, 0, 1, 2, 3, 4, 5, 6, 7.
But that's true, but it's the relationship that I'm looking for. And I'll write an example, and maybe this example will help explain what it is that we're looking for. Let's say that we had the number 1, 4, 2, 3, base 8. What this is equal to is 1 times 8 to the 3rd power plus 4 times 8 squared plus 2 times 8 to the 1st power plus 3 times 8 to the 0. So we're relating all these digits to powers of 8 and multiplying. So what do we know about the units digit separate from everything else?
No matter what, the unit digit doesn't change when you move from decimal to another base. This is a factor multiplying it essentially against 1.
The units digit does change, and here's an example. The number 1, 2 in base 8, that's 1 times 8 to the 1st, that's 2 times 8 to the 0, which is just 10 in base 10. So the units digits can change. They usually do.
All the unit digits are remainders.
They're remainders. Very good. Yeah. This number right here is 8 times 1 times 8 squared plus 4 times 8 to the 1st plus 2 times 8 to the 0. It's 8 times an integer plus 3, which means that it is congruent to 3 modulo 8. It's 3 more than a multiple of 8. So the units digit the units digit in base 8 gives us the residue modulo 8, at least for a positive integer, a natural number. So what are all the units digits of perfect squares in base 8?
So shouldn't it be 0 through 7?
It's not 0 through 7. Perfect squares cannot have a units digit of 2 in base 8, for instance.
Is it 0, 1, and 4?
That's right, Salarm. How come?
Well, what I did is that I tried to square some of the values to figure it out. So I started 1 squared is 1 in base 8, 2 squared is 4 in base 8, 3 squared is 0, 1 in base 8, and 4 squared 0, 0, 0, 0 in base 8. And so I realized that it was just giving me values that were that basically repeat themselves. So I ended up coming to that conclusion.
Okay. So you squared some numbers to see. How does it help to relate this to mod 8? I mean, what did we show earlier about perfect squares modulo 8?
The perfect squares, they had residues that were 1, 4, 0.
Right. And those are the units digits in base 8, aren't they?
Yeah.
So what about in base 7? What are the possible units digits of the squares?
0, 1, 2, and 4.
0, 1, 2, and 4. It's the same problem. Once we realize it's the same problem, well, there's less work to be done. Okay, let's move on to problem number 9. That's a lot of numbers to square. We're adding them all together. How can we get started?
Convert to base 7.
We don't need
Sorry,
to.
modulo 7.
Okay, we can work in modulo 7. Good. So what do we find when we start working in modulo 7?
That the residues repeat themselves.
Yeah, we have a lot of repetition. Where do we end? What's 2009 modulo 7?
Zero.
Yeah, it's 0.
0.
That's right. Okay, what do we do now?
We can write the values of the numbers and divide by 7.
Okay. In other words, replace the squares with their modulo 7 residues. Okay, so
Yes.
T is congruent to 1 squared is 1, 2 squared is 4, 3 squared is 2, 4 squared is 2, 5 squared is 4, 6 squared is 1, 7 squared is 0, and then we repeat over and over again. How many times do we repeat?
Well, we'd have to divide the
Wouldn't you have to divide the
sum
2009 by
the
7?
we could sum the first few residues and then multiply by the 287 and convert that into modulo 7 and see what we get.
Right. We have these same 7 terms repeated 287 times over. And we are working modulo 7. So what happens?
You get 0 mod 7.
Yeah, we just get 0. In fact, both 14 and 287 are 0. So we have 0 times 0, which is certainly 0. It is very 0. And 0 is our answer. That's it. Seems remarkably simple, right?
Yeah.
Yeah.
Yeah, modular arithmetic just takes so many calculations and simplifies those calculations for us. And, practice this, learn a little more as you go, explore, and you'll find more and more methods that just simplify so much work for you. So looking at this one, I'm going to point this out, and I don't know if any of you have ever seen this formula before. We could do this problem in another way, knowing the formula for the sum of the squares of the first n positive integers. Does anybody know that formula?
Wait, sorry, could you please repeat yourself?
Sure. What is the formula? I'll write it down. What is the formula for the sum of the squares of the first n positive integers? Okay, if you haven't seen this before, I'm going to go ahead and write it. And in a couple of weeks, maybe we'll see if we can prove this when we're doing algebra. I won't do it today, but the formula here is n times n plus 1 times 2n plus 1, all divided by 6. And it's kind of, when you first...
Tetrahedral sequence.
Say that again?
Isn't it I think it's tetrahedral sequence.
Yes.
The form, that's the form.
Tetrahedral, okay. I know that we can back it out of tetrahedral numbers. That's true. That wouldn't necessarily be the way that I would do it, but we could. The sum of squares right here. And notice, it's not that hard to memorize because those first two terms, those are in our formula for triangular numbers. 1 plus 2 plus 3 all the way up to n is n times n plus 1 divided by 2. So we have those same two factors, and then we add them. 2n plus 1 is n plus 1. And then instead of dividing by 2 down here, which is 2 factorial, we divide by 3 factorial. And we'll find out whether factorial really is or is not what's going on down there. But if we used this formula, then we could say,
Mr. Crawford.
Yes.
I remember for one of the assessment works we did in school, we were trying to work with Pascal's triangle, and we were looking at the diagonals and how to show that the diagonals would give us these formulas, the n times n plus 1 times 2n plus 1, and the n times n plus 1, and so on and so forth. And we were looking at how the row at the diagonal affected it. So I think we did something like m minus 1 factorial, which was the diagonal, as our bottom denominator. And so when we went to the first one, 1 factorial is 1, and we were looking at rising factorials as well. And some people didn't use rising factorials but I recall some of that. And I was wondering if Pascal's triangle would fit into any of the things we were doing here.
Pascal's triangle fits into more of Wendy's lessons that she's working with all of you. It may be interesting just to, there are definitely things that happen with mods within Pascal's triangle. And that's a worthwhile explanation. Maybe I'll cover that some next week. I don't know if we'll have time given the lesson plans, but here's what I'm going to say first. You do that exploration. Take the numbers in Pascal and first ask, okay, what are all these numbers modulo 2? See what you get. Then ask, what are all these numbers modulo 3? See what you get. See if there appear to be any patterns. I suspect there will be. See what mods look most interesting. But I will say this, what we did last week when we did Lissandra's theorem, that may be helpful, because Lissandra's theorem helped us figure out representations, prime factorizations of factorials, and the numbers in Pascal's triangle are just combinations. Have you covered that with Wendy yet?
We haven't done it with Miss Wendy yet, but I did in school. It was how the column, sorry, not the column, row was choose n of the placement in the row. So like the first in the row would be 3 choose 0 for row 4, which would give us 1, and then 3 choose 2, 3 choose 3, 1, and so on and so on.
So good. So you're part of the way there. So the numbers in Pascal's triangle are combinations, and combinations are factorial times factorial, or factorial divided by factorial times factorial. And Legendre's theorem tells us how to count up the number of prime factors of each prime in there. And then modular arithmetic allows us to take powers of primes and reduce them in any modulus that we like. So the table is set. You have all the tools. I'm going to let you explore that. Maybe sometime down the road, whether it's during this 6 weeks or in the future, I may make a video on just this topic if we don't get there. And I don't think we'll have time to get there, given my lesson plan. But I will, sometime, maybe I'll have time this month or next, but it might be a little bit down the road. Either way, continue to go look at these videos where I post them on YouTube, and you're likely to see that and other topics pop up. Okay, so we have a formula for the sum of squares. And I just want to point out, we already know that this must be an integer, right? We don't have to think about whether it's an integer. So all we really need to do is notice that 2009 is a multiple of 7. And we know that 7 will be in the prime factorization of the result. And that tells us that we have something that is 0 mod 7. Okay, let's take a look at problem 10. This is interesting. This actually relates to the Pythagorean theorem, kind of. What do we call solutions to this equation that are integers. Have any of you heard this term before, Pythagorean triple?
Yeah.
Yeah, kind of.
Yeah, what's an example of a Pythagorean triple?
3, 4, 5.
What's another?
12, 7, and 13. Or is it? I think it's. I know it's 12 something and 13.
True. What's 13 squared minus 12 squared?
Let's say 10.
169 minus 144. Of 12, 5, and 12, 5, and 13.
Mm-hmm. Here's another one. 8, 15, and 17. Well, one way of interpreting this problem is that we are going to prove that a Pythagorean triple cannot have all three numbers odd. There has to be at least one even number in there. How do we know?
So, Mr. Crawford, the Pythagorean triples, is it saying that when you squared two different integers and they sum to give you another squared form of another integer, that's basically the Pythagorean triple?
That's correct. That's what a Pythagorean triple is.
Then
Okay,
you
thank
can draw a triangle and put the numbers like in it and try to square them to see whether you get the same result.
Yeah, it
Yeah,
has to. Go ahead.
Oh, you go ahead.
It has to be specifically a right triangle. The Pythagorean, the way I learned it was the Pythagorean theorem was meant to find out that the diagonal of a square or a rectangle.
Yeah, and I'll put it a different way. When you say, it's meant to find the hypotenuse or meant to find a diagonal, I would say don't view this as a formula. View it as an identity. And I don't know if you've heard that term before.
No, I haven't.
An identity, well, it can be an equation, certainly, but what it means is that both sides are equal regardless of the values of any of the variables. And in this case, it does assume that we're talking about a right triangle, but we don't just compute the hypotenuse from the sum of the squares of the legs. We could compute the value of a leg from the value of the other leg in a hypotenuse. So the reason I mention that is because a lot of times we begin to learn formulas early on in mathematics and we think, oh, I'm always computing this. Well, you're not always computing that. Sometimes you're computing other pieces of it and you can use the whole thing, right? We could solve for A or B instead of solving for C. And here's an example. What if B equals 40 and C equals 41? Somebody tell me what A must equal.
(41 squared minus 40 squared). So that is
The answer is 9.
yeah.
Yeah, 41 squared is 1,681 minus 40 squared, which is 1,600, gives us 81, and 9 squared is 81, and that is another Pythagorean triple.
Yeah.
Are there infinitely many Pythagorean triples?
Yes,
How do you know?
because you could create a Pythagorean triple with any two numbers. Let's say we choose 6 and 7. No, my bad.
I think
Because
6, 9, 25.
What was that, non-Norley?
Choose 6, 9, and 5.
What do you mean choose 6, 9, and 5? Choose them to do what?
Sorry, like you can choose 16, 9, 25. When you add 16 plus 9, you get 25. So the 25 could be C, which is the hypotenuse. And then the 9 or the 16 could be A or B.
Oh, you're talking about the 3, 4, 5?
Yeah.
Okay. What can we do with those numbers 3, 4, 5 to get another Pythagorean triple?
Multiply like all of them by a common number. It's like
Yeah.
ratios.
So if 3 squared plus 4 squared equals 5 squared, then 3t squared plus 4t squared is equal to 5t squared. And we call all of these, we call them 3, 4, 5 right triangles when we find them, right? 3, 4, 5, 6, 8, 10, 9, 12, 15, infinitely many of them, and we just call them all 3, 4, 5 right triangles. So now here's another one. Instead of just talking about Pythagorean triples, we can talk about primitive Pythagorean triples. Now 3, 4, 5 would be said to be primitive, while 6, 8, 10 is not. A Pythagorean triple is said to be primitive when each two of the three numbers is pairwise relatively prime, which means they don't have a common divisor greater than 1. So these 4 are all primitive. Now I might ask the question, are there infinitely many primitive Pythagorean triples, where we can't just use this method to generate more and more of them, because anytime we plug in like t equals 2 or t equals 3, we create that as a common divisor among A, B, and C. For primitive Pythagorean triple, I'll use PPT for short. And here are 4 different PPTs. We've already talked about 3 of the 4. What do we notice about these?
They all contain prime numbers. At least one prime number.
That's true. They all contain at least one prime number.
There's at least one even number.
And at least one composite number.
There's a multiple of 4 in each of them.
That's true. The middle number is a multiple of 4. It is composite and even. Good. What else?
The first number on the left keeps increasing by 2. 3 plus 2, 5. 5 plus 2, 7. 7 plus 2, 9.
And the last number increases by 8.
Not always 8, but it does seem to be increasing by a regular amount. Okay, keep going. What else?
The increasing rate of the last number is the same for the middle number.
Sorry, I couldn't understand.
The increasing rate for the last number is the same for the middle number.
Oh, that's true. Yeah, the middle numbers are increasing by the same as the last number. What's going on there? What's the relationship between the last two numbers?
They have to have the same tens. It seems they have to have the same tens digit.
Maybe.
They all have a difference of 1.
They are all separated by just 1. Okay, their differences are just 1. I want to point something out. We usually write the Pythagorean theorem as a squared plus b squared equals c squared. But if we wanted to, we could rewrite it as c squared, as a squared equals c squared minus b squared. And how does c squared minus b squared factor?
Oh, the difference of squares. So it's c plus b times c minus b.
Okay. Well, what happens if c minus b equals 1 every time?
Then it's just c plus b.
That's right. For all of the ones that I've written on this page, what I did is I picked out examples where c minus b equals 1. And then notice what c plus b equals. What's 4 plus 5?
9.
9 is 3 squared. What's 12 plus 13?
25. That's 5 squared.
That's right. 24 plus 25?
49. So 7 squared.
And 40 plus 41?
81. So 9 squared.
That's right. Does this pattern continue? Are there two integers that are 1 apart that add up to 11 squared?
Could it be 60 and 61?
60 and 61.
That's right. Build me one with 13.
$84 and 85.
Okay, so let's describe all of these at once. We're starting with an odd integer. And then how do we get the other two numbers?
We divide the square of that odd integer by 2 and round down, and then we add 1 to get the next number.
That's right. What's 4n plus 1 squared?
It's 2n squared plus 4n plus 1.
You're close. What's the first term?
4n squared. 4n squared plus 2n plus 4n plus 1.
I think you were already jumping to what comes next. How do we divide this up into part B and C? What we want is for B plus C to be the square of A. So we want B plus C to be 4n squared plus 4n minus 1, but we know that C minus B equals 1. So what are B and C in terms of n?
It will have to be minus 4n squared minus 4n.
What if we add these two equations together? What do we get?
C.
4n squared plus 4n plus 2.
Okay. So what is C?
C is equal to 2n squared plus 2n plus 1.
That's right. And if B is 1 less than C, what is B?
2n squared plus 2n.
That's right. Now we can write all of these types of Pythagorean triples as 2n plus 1, 2n squared plus 2n, and 2n squared plus 2n plus 1. But I'll tell you, I don't quite do it this way. I do it, I don't know if it was Salorm or David, I can't remember who said it, but they said, hey, we can square this number, then divide by 2, round up and round down. So if I want to build one out of 15, where n equals 7, perhaps, I would square 15. I'd get 225. I would divide that by 2, and then I'd round up and round down, and I know that 15, 112, 113 makes a primitive Pythagorean triple. And we can do this for any positive integer n, so we have infinitely many primitive Pythagorean triples. And I just want to point out, these are not all the Pythagorean triples, but since there are infinitely many of these, we know there are infinitely many Pythagorean triples. Any thoughts about this? So let's go back now to the original problem that started this wonderful discussion. We were trying to prove that we can't have a Pythagorean triple with 3 odd numbers. Oh no, we weren't proving that, excuse me. I kind of jumped, I kind of made that leap myself, but that wasn't really what we were doing. I just kind of related that problem to Pythagorean triples in a different way. We want to prove that the sum of 2 odd integers, the sum of the squares of 2 odd integers, cannot itself be a perfect square. So what do we know about the square of an odd integer? What modulus could we work in?
We could work in mod 3.
We could work in mod 3, but mod 3 is not a good modulus to talk about odd integers in specifically.
Mod 10.
Mod 2.
Possibly mod 2, but mod 2 is not restrictive, right? The square of an even number is 0 mod 2. The square of an odd number is 1 mod 2. We want a modulus that is restrictive, right? If we go back to one of our early
Mod
problems,
10.
maybe mod 10. I'm thinking something else though.
Maybe we could do mod 11, since 11 is greater than 10, which allows for a greater value, greater numbers for us to choose from. But at the same time, it still remains an odd number.
I don't like 11 because it doesn't mesh with the information in the problem. The information in the problem is that we're talking about squaring odd numbers. And I want to find a modulus where I know about the squares of odd numbers simply and easily. Which among these?
mod 8.
Mod 8 is a very reasonable candidate. Modulo 4, however, is a little bit simpler. So let's take a look. If we square an odd number, we necessarily get 1 modulo 4. And I'm cheating very slightly here, but I'll fix the cheat in a moment. We always get 1 mod 4. What happens if we add, if we say a squared is 1 mod 4, and b squared is 1 mod 4. What is a squared plus b squared mod 4?
2.
2. Okay, why is that interesting?
Because 2 is an even number.
Okay, it's an even number, but we're trying to prove that the sum of 2 square odds cannot be a perfect square. So why is 2 mod 4 interesting?
2 mod 4 is not part of the residues we can get for perfect squares.
Exactly. Good work, Salorm. A squared plus b squared, a perfect square, n squared, can only be 0 or 1 mod 4. So this cannot be a perfect square. Now, I told you a moment ago that I cheated just a little bit. Here's how I cheated. I said that an odd number must be 1 or 3 mod 4, but I didn't justify that yet. But let's see. An odd number can be written in the form 2n plus 1 for some integer n, and I'll take 2 cases. N is either an even number, in which case I can write it as 2k, and we get 4k plus 1, which is 1 mod 4, or I can write k as 2k plus 1 because it's odd. Sorry, I can write n as 2k plus 1 if n is odd, and then we get 4k plus 3. So yeah, an odd number is either 1 or 3 mod 4. And here's one more way to think about it. The square of an odd number can be written this way. And that's equal to a multiple of 4 plus 1. Therefore, it is congruent to 1 mod 4. Okay. So I've got a few other problems here, and they're a little on the harder side. I recommend giving them a try. Yes.
Because I'm wondering why we had to use mod 4 specifically if we could have come to that same conclusion using all other types of mods because of their set value of squares that are possible. I mean, there are some of them that we discovered have all, but the ones that have a distinct number, couldn't we have also used those ones instead of using mod 4?
There are probably other mods. In fact, I know there are other mods that could have been used. We could have used modulo 8. But I used modulo 4 just because it's simpler. The numbers are smaller. There's just, 0 and 1 are the only possible residues of squares. And so that leaves us with less work to do.
Okay.
Very, very often in mathematics and modular arithmetic, we'll find more than one way to do something. And that's totally fine. But we'll try to gravitate toward the simplest or at the very least, understand the mechanisms of all of them. Actually, I think that's most important, is to understand all the mechanisms and have all available options at our disposal. So we're going to go ahead and jump forward a little bit and talk about divisibility rules. And divisibility rules are something that all of you already know at least a little bit about, right? If I asked you whether the following number is even or odd, it's easy. Here's the number: 262,974,413,222,763. Is that even or odd?
Odd.
Odd.
It's odd.
Odd.
You all know that it's odd pretty quickly. How come?
You just have to check the units digit.
We just have to check the units digit. So we have a very simple divisibility rule to test whether or not an integer is divisible by 2. We have a few other simple divisibility rules. It's easy to tell if an integer is a multiple of 5. How do we do that?
It either ends in 5 or 0.
Yeah, the units digit has to be 0 or 5. And how do we know if an integer is a multiple of 10?
It has to end
Always
in
ends in 0.
It has to end in 0. Right, the units digit must be 0, which is, it's a combination of the divisibility rules for 2 and 5, right? Divisibility rule for 2 says units digit is even. Divisibility rule for 5 says it's a multiple of 5. And 0 is the only even multiple of 5 that is a digit. So ultimately, I'm going to write that out in terms of modular arithmetic. Even though this is simple for all of you, this is going to help us discover more interesting divisibility rules. So if I take a number, let's see. If I take a number n and I write it as the sum of base 10 digits, then we examine this modulo 5, for instance. What is this number modulo 5? What is
It's going to be 0 because of the fact that we are combining the divisibility rules for 5 and 2 to make multiples the 10.
We don't need to cite the divisibility rule. We can work in modulo 5. Right? 10 is 0 modulo 5. So if we work in modulo 5, we replace 10 to the k power with 0 to the k power. We can replace 10 to the k minus 1 with 0 to the k minus 1. The only one that we don't get rid of this way is the units digit.
So, Mr. Crawford, does this mean that this number would be D0 mod 5?
Right. What we're demonstrating here is that an integer is congruent to its units digit modulo 5. And this instantly proves our divisibility rule for a multiple of 5, right? If we want a multiple of 5, we need that units digit to be a multiple of 5, so 0 or 5. And we used mod 5, but we could have used other mods. We could have used 2 or 10. An integer is congruent to its units digit mod 2, and an integer is congruent to its units digit mod 10. And you might ask, why are we going through this amount of pain to look at it that way? Well, it's because we're going to use the same idea to build more advanced divisibility rules. Suppose I wanted to know, and actually, I'll say one more thing. It's not even just a divisibility rule. It's more powerful than that. This is a remainder rule, right? We don't just know that 135 is a multiple of 5. We know that 137 is 7 mod 5, so it's 2 more than a multiple of 5, right? Not just a divisibility rule. It's a remainder rule, as we see it in modular arithmetic. But what if I wanted a remainder rule or a divisibility rule for 4? How can we tell quickly whether or not the number 133,752 is a multiple of 4?
Must end in 2, 4, 6, 0, or 0.
Okay. Here are 2 consecutive even numbers. Only one of them can be a multiple of 4. Which one? Let's start with the first one. This is that number written out in terms of digits times powers of 10. If we examine this modulo 4, what happens?
Well, if we convert the powers of 10s into modular 5 and we solve, then we are left with 2. We're left with 2, and when we have 2, we put it into, we take it from mod 5 into mod 4, and it tells us since there's a residue of 2, it can't be divisible by 4. Otherwise, it would have a 0 as a residue.
Okay, it sounded like you were going in the right direction, and then I lost understanding of how you were saying it. So tell me if we are looking at things in a similar way. A lot of these terms are already multiples of 4. But the last 2 might or might not be. Ten squared is 2 squared times 5 squared. And 2 squared is just 4, so that's 0. Modulo 4. What did we just learn? Right, we're
We
examining.
just learned that this is the first one is divisible by 4. 132,000, that is, times 132,752 is divisible by 4, because of the fact that when you break it down into powers of 2 and 5 against its different integers, and you're left with the sum of the last two digits. And depending on the sum of the last two digits, it will determine whether this number in mod 4 would give us a multiple of 4 that's divisible.
That's very, very close. You've got the right idea. It's not the sum of the last two digits. It's just the last two digits is a standalone two-digit number. What we've proved here is that an integer, well, what we would prove if we wrote this out more generally, is that an integer is congruent to let's see, let's say that m is the two-digit number formed by the last two digits of n. And again, n is a natural number as usual. So n is, we can just simplify it to its last two digits. So for instance, 52 is a multiple of 4. Therefore, 133,752 is a multiple of 4. However, 54 is not a multiple of 4. It's 13 times 4 plus 2. It leaves a remainder of 2. Also, 133,754 leaves a remainder of 2 when divided by 4. Make sense?
So essentially, we just have to convert the last two digits into mod 4 every time to find out whether it's multiple of 4.
There you go. That's right. So to determine whether an integer is a multiple of 2, 5, or 10, we just need one digit, just the units digit. If we want to know whether a number is a multiple of 4, we use the last 2. Can you think of another modulus where we could use the last two digits?
Mod 8.
For mod 8, we need the last 3 digits. Why would that be?
Because it has 3 powers of 2.
Powers of 2, we are talking about powers of 2. We're definitely coming up with a rule for powers of 2. We're going to have some other options also. How can we tell if an integer is a multiple of 25?
If it's a multiple of 5 that is greater than 5 squared.
Yeah, I don't know what that means though. How many digits do I need?
Just the last digit. It must end with either 5 or 0.
That's not enough.
The last three digits.
35 is
Last two.
5, but it's not a multiple of 25.
The last two digits, if it's either 25 or 2 zeros.
Why the last two digits?
Because I think it was a couple of lessons back, we found out that when you squared when you squared, you'd always have 25 as the last two digit every time.
Huh.
You'd have, and when
The multiples.
I like that you're trying to relate things to previous lessons, but we were talking specifically about perfect squares there. But you're right; those squares did end in the last two digits 2, 5. But go ahead. Who else was giving an idea?
Me. The multiples keep appearing, like you get 25, then 50, then 75, and 2 zeros, and they keep on using the same pattern.
Okay, we could think of it as a pattern. However, in modulo 100, everything prior to the last two digits just turns into nothing because we're multiplying it by 0. Because 100 is 0 mod 25. right? We can do this in any modulus that is a divisor of 100. And that means that we only need the last 2 digits. So last 2 digits give us a divisibility rule for 4, for 25, for 20, for 50, right? You can instantly tell whether or not the number 133,740 is a multiple of 20. Is this a multiple of 20?
Yes,
How come?
because when you multiply it by 0, it's the same thing as times 0 plus 40, and 40 is a multiple of 20.
Okay, yeah, just the last 2 digits matter.
Yeah.
Everything else is a multiple of 100, and 100 is already a multiple of 20. So now, somebody brought up divisibility rule for 8. How many digits do we need to look at to tell whether or not an integer is a multiple of 8?
3.
The last 3, how come?
Because
8 is the
if we
divisor of
follow
what
the
number?
method by multiplying by 100, in this case we multiply by 1,000, which is, and when we multiply by 1,000, we're able to put in mod 10, 1,000 into mod 8, and that's 0. So all we have left are the final 3 digits.
And in this case, 752 is a multiple of 8. And therefore, the original integer was a multiple of 8. Very good. So sounds like you're picking it up. This was even quicker than the divisibility rule for 4. So you see the pattern. Now we can come up with a divisibility rule for any power of 2 or any power of 5 or combinations of powers of 2 and powers of 5. We just need to group out as many digits as necessary to separate out a multiple of the modulus that we're working in. So we can invent whatever divisibility rule we need on the spot.
Can we try for 6?
So not yet, because we need to conjure a divisibility rule for 3. What is the divisibility rule for 3?
You must add all the numbers and they must be a multiple of 3.
Okay, so we're about to show this for 3 and 9. And I want to point out that we didn't get through all the problems today, but here's your homework. Work as many of the remaining problems that are here and try to figure out a divisibility rule for 11, or actually maybe I'll just state it and then leave it as something for you to try to prove. But try to work as many of the exercises remaining in this document, the Ghana number theory 3 modular arithmetic document. But let's take a look at divisibility rules for 3 and 9. If I were to take the number 133752, I'm going to write this out in terms of the values of its digits. But let's think about this mod 9. What makes this easier, mod 9?
You just need to add the numbers.
Look at those powers of 10. What's interesting?
They decrease 5, 4, 3, 2, 1.
Yeah. What's interesting about them modulo 9?
Mr. Crawford, did you see something?
10 raised to the power 0 modulo 9 is 1. 10 raised to the power 1 modulo 9 is... Sorry, 10 raised to the power 0 modulo 9 is 0. 10 raised to the power 1 modulo 9 is 1. So it
Hello?
keeps increasing.
Very good, non-gnarly. Can you all hear me? It sounds like Salorm can't hear me anymore.
Yeah, I can hear you.
Okay.
Salorm, can you hear me?
Okay, so let's talk about what non-Norley just told us. Non-Norley just pointed out that all of these powers of 10 are just 1 mod 9.
So that's why you can add them up, and then if that's divisible by 3, then the original number is divided by 3.
Right. This works both modulo 3 and modulo 9. Why does this work in both mod 3 and mod 9?
Because in mod 3, 10 is equal to 1, and in mod 9, 10 is equal to 1.
That's right. Exactly. 10 is 1 more than 9, which is both a multiple of 3 and a multiple of 9. And notice, this is both a divisibility rule and what else?
A divisibility rule.
It's a divisibility rule and it's a remainder rule, right? We didn't just learn that 133,752 is not a multiple of 9. By adding the digits up and simplifying, we found that this is exactly 3 more than a multiple of 9. Right? And that's better because sometimes we may need to know the remainder. We may need to know the full relationship. So not only, the sum of the digits, if the sum of the digits is a multiple of 3, the original integer is divisible by 3. If it's a multiple of 9, the original integer is a multiple of 9. But whatever it adds up to, let's say that S of n is the sum of the digits. The remainder, when n is divided by 9, is the same as the remainder when Sn is divided by 9. So divisibility rule, remainder rule. Now, real quickly, does anybody know a divisibility rule for 11?
It would be that it repeats from 1 to 0.
I'm going to leave this as an open question.
So the last digit in the number ends in 1, there's a chance that it could be divisible by 11.
So not quite. This one's going to be a little bit more complicated, but we will leave this for another time. I'm going to say make that part of your homework. See if you can think through a divisibility rule or a remainder rule for 11. And remember what we did here modulo 9. We looked at powers of 10 modulo 9. That's a hint. See what you can do between now and Monday. Any questions? Then I guess I will see you all on Friday for office hours.
All right, bye.
Take care.
Hey, thank you, Mr.
Mr.
Crawford.
Crawford,
Bye.
please,
You're welcome.
Thank you. Bye.
Thank you.
please can you go through the Pythagorean triples?
To go through the Pythagorean triples, that's a pretty long discussion. I usually do that in a more advanced number theory class once we've added a few more tools to our toolkit and developed this for a while longer. But I'm going to say, hey, if you want to explore that, go after it. Play around with other Pythagorean triples and see what you discover. And one hint might be, remember when we rearranged the Pythagorean triples, we rearranged the Pythagorean theorem. Let me see if I can find that. We rearranged it in order to factor one side. This factorization may lead you to other relationships with Pythagorean triples and possibly the ability to just invent them on your own.
Okay.
Right. Any other questions? If not, I will see you all on Friday. Take care.